11, we're going to go over implicit differentiation. Implicit differentiation is a way that we can take derivatives without first solving for y. Sometimes we could solve for y. Sometimes we're not going to be able to. In this first example, we want to find the slope of the tangent line to the circle at the point 4,3. And the equation of the circle is x squared plus y squared equals 25. So we could go through, we could solve this equation for y. So we get our pencil here, we get x squared plus y squared equals 25. We're solving for y. We're going to subtract x squared from both sides. So we get y squared is equal to 25 minus x squared. Take the square root of both sides. Typically, when we're solving an equation, and we take the square root of both sides, we would include the positive and the negative square roots of 25 minus x squared. Now we can take the derivative of that. That's really plus or minus 25 minus x squared raised to the 1/2 power. Take derivative of that, we'd have to use chain rule. So y prime be equal to plus or minus. We're going to multiply by the exponent. We're going to leave the inside alone, 25 minus x squared. We're going to subtract 1 from the exponent. 1 minus 1/2 is negative 1/2. And we're going to multiply that by the derivative of the inside function. The derivative of 25 minus x squared is negative 2x. Clean that up a little bit. The 2's cancel. We get negative x in the numerator, and we get plus or minus negative x. And in the denominator, we get the square root of 25 minus x squared. This plus or minus can just, the negative can be taken up into this plus or minus, so we don't really need the negative there. All right, then we're going to plug in 4. So we get y prime of 4, because we're trying to find the derivative at 4,3. So y prime of 4 is going to be equal to plus or minus, we get 4 on top. Square root of 25 minus 4 squared is 16. 25 minus 16 is 9. The square root of 9 is 3. So we get positive or negative 3. It can't be both. We have to look over here at the point 4,3. If we were to sketch that tangent line, that slope would be negative. So we would pick the negative answer in this case. So in that case, what we just did, we would call explicit differentiation right here, explicit differentiation. And this process is accomplished by getting y by itself. And in this case, it was possible to get y by itself. We did see that we ended up with 2 answers, but only one of those answers was correct. And we would have to depend on the knowledge of our graph to figure out which one of those to use. Sometimes we're not going to be able to solve for x, and we're not going to know what that graph looks like to determine if we're going to get a positive or a negative answer. So we may need implicit differentiation. Something like x squared plus y equals 2. Solving that for y would be quite complicated. We could try. We could subtract x squared from both sides. Subtract x squared from both sides, and then we get y to the 3rd plus y equals 2 minus, what am I thinking? That's x squared, not 2x. So we would subtract x squared from both sides. Then we get 2 minus x squared. Y to the 3rd plus y, there's no way we can really combine those. We could try to factor out a y, but then we get y squared plus 1. That doesn't really do us any good. So solving for y here would be very, very difficult. So we need another way that we can actually take this derivative, and that would be this method of implicit differentiation. So what we're going to do is we call it the derivative dy dx, and we're going to use that derivative of x, we're going to call dx dx, and we're going to use that in this process of implicit differentiation here so that we can see. So we're going to find dy dx for x squared y squared equals 25, and we're going to do that using the implicit differentiation. So we can take derivatives of every term, remembering the chain rule. And if we take derivative with respect to x, we're going to put dx dx. And if we take derivative with respect to y, we're going to put dy dx. So looking at x squared, what is the derivative of x squared? Derivative of x squared is 2x. And since we took the derivative of x with respect to x, that'd be dx dx plus derivative of y squared would be 2y, but we took the derivative of y. with respect to x, dy dx. And that equals the derivative of 25. Derivative of 25 is 0. We can get rid of the dx dx. It's just really 1. Dx dx is just 1. So from now on, we may or may not write the dx. I might write it sometimes, but dx over dx is just 1. So really, we get 2x plus 2y dy dx is equal to 0. All right, so we get 2x plus 2y dy dx equals 0. Now we can plug in our point and solve for dy dx. The point was 4, 3. So we're going to plug in the point 4, 3. So anywhere there's an x, we're going to put a 4. Perhaps. So we get 2 times 4 plus 2 times 3. Dy dx is equal to 0. And then at that point, we can solve for dy dx. 2 times 4 is 8. 2 times 3 is 6. We're going to treat dy dx just like a variable, just like we were solving in an equation. We subtract 8 from both sides. We get 6. Dy dx is equal to negative 8. We divide both sides by 6, and we get our derivative, dy dx. Typically, we would write this this way, dy dx at the point 4, 3 is equal to, and we see that the negative took care of itself here. Negative 8 over 6 does simplify to negative 4 over 3. So we see we got the same answer as before, negative 4 over 3. But we didn't have to worry about what's the sign. The sign just took care of itself. We didn't have to solve for y either. Note we didn't actually find dy dx. We found dy dx at a point. If we have to find dy dx, an expression for dy dx, we would just go through and solve for dy dx before we actually plug the numbers into the equation. And they've done that for us right here. They subtracted the 2x from both sides. Then they divided both sides by 2y here. They divided both sides by 2y. And then they simplified the 2's, and they got negative x over y. We'll see a lot of examples like those in a little bit where they actually go through and solve for dy dx before they plug the number in. But again, we're just going to treat that dy dx like a variable, and we're going to get it by itself. So now we're going to take the same dy dx equals negative x over y, and we're going to find the tangent line at a whole bunch of points. So dy dx at 3, negative 4 is going to be negative 3 over negative 4, which is just 3 over 4. So it's really easy. Once we get the point, we don't have to solve for dy dx over and over again. We can just plug these in. So we want the point negative 221. So our x value is negative 2. So we get negative 2 over the y value, square root of 21, which is 2 over square root of 21. And if we want to simplify that denominator so it's rational, we multiply top and bottom by square root of 21. So we get 2 square root of 21 all over 21. About the point 0, negative 5. So we would get negative, technically 0 over negative 5, and 0 on top with a number on bottom. It's just 0. What about negative 5 over 0? We get negative 5 over 0. We can't divide by 0. So the tangent line at D, the tangent line at the point negative 5, 0 does not exist. And the reason it doesn't exist in this point, it would be a vertical tangent line. And we'll talk about those a little bit later too in this chapter. And if we go back up and look at negative 5, 0, you will see that that is a vertical tangent line at that point. Alrighty, rolling on. Number 1, we want to find dy dx for x squared minus y squared equals 16. We could go through and solve this for y. We don't really want to. So we're going to take the derivative of each piece using the rules that we've learned in the past. Anytime we take derivative of x, that's dx dx, which is just 1. So we're probably not going to write it every time. But anytime we take derivative with respect to y, we got to write y dy dx. So derivative of x squared is 2x. And I'm going to write the dx dx a couple times, but then I'll get out of the habit of writing that. Derivative of y squared is 2y dy dx. We absolutely have to write that one. If we don't write that one, we might as well stop. And that's equal to 0. And at this point, we can go ahead and plug in the 0.5, -3 if we want. The dx is going to cancel. So we get 2 times 5 minus 2 times -3. dy dx equals 0. And if we're just asked to find this at one point, we might as well go ahead and plug the point in before actually solving for dy dx. So we get 10 plus 6 dy dx equals 0. Subtract 10 from both sides. So we get 6 dy dx equals -10, and divide by 6 on both sides. So dy dx at the point 5 -3, sometimes we write it this way, 5 -3 is equal to -10 over 6, which simplifies to -5 over 3. Number 2, find dy dx for xy plus y equals 9 at the point 2, 3. This xy is going to be a product, so we're going to have to use product rule. So we're looking at f prime g plus g prime f. It would help to probably like memorize what derivative of xy is, because this can show up a lot in the future. Derivative of x is 1, and since we took the derivative of x, that's dx dx times g would be our y value, plus g prime, the derivative of y, would be 1 dy dx times the f, which would be x, plus y, the derivative of y, would be 1 dy dx equals derivative of 9 is 0. We don't have to write the dx dx. So if we clean this up a little bit, we get y plus dy dx times x, or we can put the x in front. So derivative of xy, something just to know, where we don't have to work it out every time. Derivative of xy would be y plus x dy dx. Plus dy dx is equal to 0. And now if we want to find this derivative at the point 2, 3, we plug that in. Y value is 3, the x value is 2, dy dx plus dy dx equals 0. We can move the 3 over to the other side, and at the same time, 2 dy dx and dy dx's can combine into 3 dy dx's, and that's equal to -3. We can divide both sides by 3, so we get dy dx at the point 2, 3 is equal to -1. Alrighty, number 3. dy dx for x squared y plus xy squared. So we got a product rule here and a product rule here. So we're going to be using product rule twice, f prime g plus g prime f. So derivative of x squared is 2x, but we took that derivative with respect to x, so I'm not going to write the dx dx. Plus the derivative of y is 1 dy dx. We have to write that every time. And we're not going to change the x squared this time because we didn't take the derivative of it. So that's just x squared. So this is our f prime g, and our g prime f. All right, plus we're going to do the same thing with xy squared. Derivative of x is just 1 dx dx y squared. We don't need to write the dx dx, plus x times the derivative of y squared would be 2y dy dx. And that's equal to, we got 2x on this right side this time. We had 0 earlier, not 0. We had a constant like 25, and the derivative of that number was just 0. But the derivative of 2x is not 0. It's 2 dx dx, and we don't have to write the dx dx this time. All right, at this point, we can just plug in 1, 1. So we get 2 times 1 plus dy dx times 1 squared plus 1 times 1 squared plus 1 times 2 times 1 times dy dx equals 2. Anything with a dy dx in it would be like terms, and all the other numbers would also be like terms. So we're looking at 1 dy dx, and 1 times 2 times 1 would be 2 dy dx. So we have 3 dy dx's all together. And we have 2 times 1, which is 2, and 1 times 1 squared, which is 2. Which is 1, and 2 plus 1 is 3. And that's equal to 2. And then we subtract 3 from both sides. So we get 3 dy dx is equal to -1. We divide both sides by 3, and we get dy dx is equal to -1/3. That would be our derivative slope of the tangent line of this curve. This curve is going to be, you can type in Desmos exactly like it looks. It's probably not going to be a function, probably going to be some cool looking curve, but the slope of the tangent line at 1, 1 is -1/3. Where did number 4 go? Where did number 4 go? Oh man, I have to edit that out too, huh? Yep. Number 4. All right, we're still recording. We're still screen sharing. All right, number 4, we got y plus square root of xy, which is xy to the 1/2 power. We're going to be using some chain rule for that. So let's go ahead and jump into this implicit differentiation for number 4. The derivative of y is just 1 dy dx, plus we got to use chain rule here. Derivative of something to the 1/2 is 1/2 times that something raised to the -1/2. But then we have to multiply all that by the derivative of that something. So what's the derivative of xy? I told you this was going to show up again. If we go back up here, the derivative of xy right here, y plus x dy dx. And we can just transfer this down. Y plus x dy dx. If you remember that, we don't have to actually work it out every time, but sometimes you're going to forget and you should be able to work it out. Derivative of 4 is 0. Alrighty, rolling right along. Dy dx 1/2 xy to the -1/2 times y plus yeah, I think we're there. All right, so we're going to plug in 2, 2. So we get dy dx. I'm going to go ahead and make this xy move to the denominator. So we get 1/2. I'm going to go ahead and change it to a square root. 2 times 2. And then we get 2 plus 2 dy dx right here. Alrighty, let's see what's going to happen here. We get dy dx plus, this is 1/2 times square root of 4, which is 2, and 2 times 2 is 4, so that'd be 1/4. And then we get, this is being multiplied times 2 plus 2 dy dx. And that's still equal to 0. Distribute our 1/4 in this case. We get dy dx plus 1/4 times 2 is 1/2 plus 1/2 dy dx equals 0. We can combine some like terms. Dy dx plus 1/2 dy dx. We got 3/2 total dy dx. And this positive 1/2, we can go ahead and subtract from both sides. And we end up with -1/2. And then to get rid of the 3/2, we can multiply by the reciprocal, which would be 2/3. And if we do that on both sides, the 2's are going to cancel out. So we get our final answer, dy dx is equal to -1/3. That's for number 5, number 4 rather. All right, number 5, dy dx for x plus y squared plus y equals 15 at -3, 1. We're going to be using some chain rule right here, x plus y to the 2nd power. So derivative of that would be 2 times x plus y to the 1st power times the derivative of x plus y. The derivative of x is 1 dx dx, which we don't have to write, plus the derivative of y, which is dy dx, which we absolutely have to write, plus the derivative of y is dy dx. That equals the derivative of 15, which is 0. At this point, we can go ahead and plug in -3, -1. It's easier just to plug it in from the get-go than trying to simplify anything if we're just interested in one point. If we're interested in more than one point, it might be a good idea to go ahead and solve for dy dx first. That way we're not doing that numerous times. All right, so we get 2 times -3 plus -1 would be 2 times -4, which would be -8. We can distribute the -8 to the 1 and the dy dx. So we get -8 minus 8 dy dx plus dy dx is equal to 0. We can combine some like terms here with the negative 8 dy dx and the dy dx. So we have 7 of those. And at the same time, let's go ahead and move this 8 to the other side. We get negative 7 dy dx is equal to positive 8. Then we can divide both sides by negative 7. So dy dx is equal to negative 8 over 7 at the point negative 3, negative 1. Number 6, we want dy dx for x squared plus 4y squared equals 4 at the point 2, 0. Derivative of x squared is 2x dx dx. We don't have to write that. Derivative of 4y squared is 8y dy dx. Derivative of 4 is 0. We can go ahead and plug in 2, 0. 2 times 2 plus 8 times 0 dy dx is equal to 0. We get 4 plus 0 equals 0 because 8 times 0 times dy dx, oh, that's 0. So what happened here? We end up with 4 equals 4, which is an untrue statement. So here's what we know. If we end up with an untrue statement in this case, and the dy dx cancels out, dy dx does not exist for this function or this expression, this relation, at the point 2, 0. That can mean it's either undefined, it's vertical, something along those lines. We're not really sure without inspecting a graph.